Hello students, welcome to this lecture on the other adders. Although I've written it as other adders, mainly we will talk about the carry increment adder. We will just take a revisit the carry increment adder and also have a look at the last adder that will be the carry select adder, that is called as the carry select adder. So let's proceed further. So just to revisit the carry increment adder and then to understand what is the overall delay. So what the carry increment adder does is it utilizes the previous carry out, and then simultaneously it generates the G7 is to 0, 6 is to 0, and 5 is to 0, and while the G8 is to 0 is generated. Right, with respect to the difference between the CLA, the carry lookup adder, and the CSA, which is the carry skip adder. So this G7 is to 0, 6 is to 0, has to wait for the previous carry out. So in this particular case, the moment 4 is to 0 is made available, there's an increment here, the OR gate or the plus sign here, which represents an OR gate. So the moment G4 is to 0 is generated, it gets incremented to 5 is to 0, 6 is to 0, 7 is to 0, and 8 is to 0 simultaneously. Right, so that's the difference between the carry increment adder with respect to the previous adders. Right, so the block diagram level, I think it is pretty trivial. So we have the first group of bits generating using the carry ripple addition mode, and then afterwards we have the we need to generate the sum bits as 8 is to 5, 12 is to 9, 16 is to 13, and so on. And between these two blocks, we'll be able to this particular block is going to generate its own group and propagate group generate and propagate signals. And then it is going to, it will wait for G4 is to 0. The moment 4 is to 0 is available, this will all generate G8 is to 0 here, and G7 is to 0, 6 is to 0, 5 is to 0 at the same time, so that we will be able to extract the sum bits. Right. Similarly for the 12 is to 9 and 16 is to 13 groups also. Right. So this is the PG level diagram which we had seen in the previous lecture. So I'll just take my pointer, and so this particular first 4 bits are nothing but the carry ripple addition so as to generate the G4 is to 0. And then what we had said was it will generate 8 is to 5, it will generate 7 is to 5, 6 is to 5, and of course this will be 5 is to 5. So it is all going to wait for G4 is to 0. The moment it waits, all these AND and OR gates here are represented as the green boxes. It will wait for 4 is to 0. The moment 4 is to 0 is available, then we will generate all of them, 8 is to 0, 7 is to 0, 6 is to 0, and 5 is to 0 at the same time. Similarly for the other groups also, it will 12 is to 9, 11 is to 9, 10 is to 9, 9 is to 9 are all made available. The moment 8 is to 0 is available, then we will generate 12 is to 0, 11 is to 0, 10 is to 0, and 9 is to 0. Similarly for the last group also. And so to find out the delay, we need to find out the S16 bit, how much time it takes to generate the 16th bit, the 16th sum bit, starting from the first stage. So the first stage will anyways have the TPG, the bitwise delay here. And the sum bit, it is going to have, in the last stage we will have an XOR gate. So the delay from the XOR gate, the delay from the TPG bitwise will be there. And in the middle stage, we will have this 4, AND and OR blocks delay, and then we will have, this block delay, and then this particular block delay, and then this particular block delay, right? So overall, what we have is from the delay from C input or the inputs whenever it is made available. It can also be, instead of C in, it can also be A1 to A16 or B1 to B16. And then it generates so the delay that it takes to generate the sum 16th bit is nothing but equal to the TPG, which is nothing but the bitwise in the first level, and then T XOR is the third stage where it generates or extracts the sum bits. And in between the middle stage, the second stage will take a delay of the 4 blue boxes here, which represent, each of these boxes represents AND and OR gate. And then 3 of this green boxes. So that's what I've written here. Instead of 4, I've written an n bits, and instead of 3 here, I've written k minus 1 bit. So what it really means is, for a k groups, for a 16 bits, we have divided into the k groups, where each group is of 4 bits. So in that sense, we will have it as k groups of n bits. So instead of 4 here, I will have n multiplied by and n OR gates delay, and instead of 3 here, I will have k minus 1 into the delay of and n OR gates. Right, so this is the critical path again, starting from the first level to that of the second level, where this 4 blue boxes will be there, and then this particular one, and this particular one, and then followed by the XOR gate. So that will be our critical path, so as to generate from the input side to the S16 bit. All right. So let's have a look at the carry select adder. So what we had seen is we started with the carry ripple adder, and then carry look ahead adder, carry skip adder, and then we also looked into the carry increment adder. Now let's have a look at the carry select adder. So I'm going to take an example first, and then we will go into the block level design. So let's say that I have a 4-bit addition. So I'm not taking a 16-bit or an 8-bit because it is pretty long. Instead of that, let's take a very simple example of the 4-bit addition. So let's say that I will have an A and B, which is having, A will have all 4 bits to be 1. I'm taking a very simple case, and then B bits is having all of them as to be 0. Right? Let's say that this is my, and this is my 8-bit to 5-bit addition. So what I'm considering is it's basically an 8-bit addition. And here from 4-bit to 1-bit addition, whatever is the number, right, it will generate a carry out, right, which is nothing but G4 is to 0, right? And I'm not going to write here whether it is 1 or 0 at this point of time. Let's say that I'll do the addition here, right? For 8 is to 5, so I will get, I'll get the sum bits here. And then I'll write it as sum 8 is to 5, right? So irrespective of G4 is to 0, let's say that G4 is to 0 is 0 actually. In that sense, G4 is to 0 actually has to go and then do the addition here, right? But let's say that it is 0 here, then I can easily find out what is S8 is to 5 based on the inputs A and B here, right? So based on the inputs A and B here, if I do the addition here, so I will get 1. I'll get 1 here, I'll get 1 here, I'll get 1 here, right? So this S8 is to 5 is assuming G4 is to 0 is 0, right? So similarly, can I now find out S8 is to 5 with an assumption, right, if it is 1. So if this is 1 here, then this carry out will go here, and then this 1 will make this 1 plus 1 will be 0. The carry will be propagated here, 1 plus 1 will be 0. The carry will be propagated here, 1 plus 1 will be 0. The carry will be propagated here, 1 plus 1 plus 0. And of course, as G8 is to 0 will be 1, right? But if I look into this closely, right, so I now have the sum bits, which is, quite different. Right, all of them 1 and all of them to be 0. It's actually based on the value of G4 is to 0, right? Based on the carry out coming from the lower groups, right? Lower bit groups. In this case, it is 4 is to 1, right? And similarly, I can do it for the 12 is to 9 bit. I can also do it for 16 is to 13 bit also, right? So the advantage here is, without caring for G4 is to 0 in this particular case, can I do the addition and then have the sum generated? Can I get the sums generated here? And then finally take a call, right? I have the sums, the sum bits are already generated, right? By assuming the carry input coming to this particular group, right, to be 0, generate the sum bits, and also generate the sum bits, assuming that the carry input coming to this particular group to be 1. So I will have 2 sum bits generated, right? 2 sum bits generated, and then this will go into a multiplexer. So this goes to a multiplexer, let's say, and the multiplexer select line will be whenever the G4 is to 0 is created, I will give it as a select line, and that will be the output, right? That will be the output of 8 is to 5. Right. So the advantage here is I'm actually creating the sum bits for both assuming that the carry input is 0, assuming that the carry input is 1, and both of them will be made available much earlier. The moment G4 is to 0 is made available, I will get the sum bits. Right, so it doesn't have to really depend on the ripple or the carry out to be rippled from the first bit to the last bit. In fact, the sum bits are generated simultaneously for all the groups. 16 is to 13, 12 is to 9, 8 is to 5. It is kind of generated, right, and it is kept. The moment the carry out is generated, it is going to pass through the sum bits, right? So the delay will be very less. In fact, the delay will be limited by this carry out signal to be generated, right? The moment G4 is to 0 is generated, or G8 is to 0 is generated, or G12 is to 0 is generated, we will get the sum bits, right? So now let's have a close look at this with our understanding of that particular example, right? So this is the block diagram of the carry select adder. So here what we are doing is we have two sum blocks here, and then the output is giving to the multiplexers, right? So one sum block assumes that the carry input is 0. The other sum block assumes that the carry input is 1, right? And then the sum that has been generated, this is basically the 4 bits here, because it is 8 is to 5, 8 is to 5. So it is actually, the sum bits is 4 bits, which is given to a multiplexer. In fact, this multiplexer will also be 4 multiplexers, right? Assuming that there are 4 bits to be generated. So the output of the 4-bit multiplexers will be S8 is to 5. And this sum bits coming from this particular block, which assumes that the carry input is 1, it is also given to the multiplexer second input. The select line is given by whenever this carry out G4 is to 0 is generated, right? And 8 is to 5 is generated. The moment G4 is to 0, whether it is 1 or 0, it passes this particular sum, or it passes this particular sum, right, as the sum 8 is to 5. Right. Similarly, for the next block of 12 is to 9 and the B12 is to 9, I will have two blocks. One block generates the sum bits assuming the carry input is 0. The other block generates the sum bits assuming the carry input is 1. It goes to a 4 multiplexers, and then based on the carry input 8 is to 0, we will get the real sums. Right. And similarly, we can continue it for the higher groups, for the higher order adder subsystems. Right. And notice that for G8 is to 0, and then for this G8 is to 0, or G12 is to 0, or G16 is to 0 that has to be generated, it actually uses the G8 is to 5 and P8 is to 5, right? So this is something we had already seen in our previous 3 adders: the carry skip adder, carry propagate lookahead adder, and then the carry increment adder. So it uses the same logic to generate, it uses the same AND and OR logic to generate the G8 is to 0. Right, so G8 is to 0, so G8 is to 5 is generated within this particular group of bits, P8 is to 5 is generated from this particular group of bits, and then it is fed to the AND and OR gate so as to generate the 8 is to 0. Alright, so let's do, how do we actually do this? So this is the expression for I and J. So we have used the K bit. So if it is an I and J, if it's considered to be so 8 is to 0 or something like that. So this I is equal to 8 and J is equal to 0. So what we are assuming is K is something like the bit number 5. So it uses G I is to 5, and then P I is to 5 has to be created, and then 4 is to 0 has to be created. The moment 4 is to 0 is created, this is made available. This is anyways made available by the individual subgroups. Remember that G I is to K and P I is to K, in this case it will be 8 is to 5, 8 is to P, 8 is to 5 are actually generated by the different blocks. And these are generated by different blocks, generated by the block which takes, generated by the sum block, right? So this is basically sum block which takes the carry 0, and then this is generated, the group propagate signals are generated by the sum block which takes the carry 1. Right, so just to know which block is doing what, so whichever is which takes in the carry 0, that block is generating the group generate bit, and whichever is taking 1, that is going to generate the group propagate signals. Right, so whichever block is taking the carry 1, that is going to generate the group propagate signal, and whichever block is taking the carry 0, it is generating the group generate signals. So that's what I wanted to imply in this particular slide. Right, moving ahead. So this is the PG level diagram which we have. Right, so the first stage is nothing but we have the bit level, bitwise generate and propagate signals. First 4 bits is nothing but the carry ripple addition. So 1, 2, 3, 4. So it will give me G4 is to 0. After that, let's take a look at this particular, the black boxes here. This is nothing but AND and OR gates. This is nothing but AND and OR gates, and this is nothing but AND and OR gates. All these 3 black boxes in this 3 groups are actually generating G8 is to 5. Right, this is generating 12 is to 9. This is generating 16 is to 13. So as to generate, the G8 is to 0, 12 is to 0, and 16 is to 0. Right, so the moment as 8 is to 0 or 16 is to 0 or 12 is to 0 is generated, it actually helps in selecting it. It goes into the select line of the multiplexer, and then we can easily extract the sum bits. Right, note here that it is basically the sum bits which goes into the multiplexers. Right, and it's not the generate signals which goes to the multiplexers, or the inputs of the generate signals or the propagate signal that is going to the multiplexer. The multiplexer actually gets the input as the sum bits. Right, so that's why you will notice that in the multiplexer which we will draw now in the next slide, it will not come in the second stage of the design. Right, it will actually come in the third stage of the design, because that is generating the sum bits. Right, so that's about this 3 black boxes here. The 3 black boxes are generating basically the individual groups generate and propagate signals. So G8 is to 5 as well as P8 is to 5. Here also G12 is to 9 as well as P12 is to 9. Here also G16 is to 13 as well as P16 is to 13. Right, and it goes into this red boxes and an OR gates, so as to generate 8 is to 0, 12 is to 0, and 16 is to 0. Right, so the moment 8 is to 0 is made available, it goes into this particular the stage where the XOR gates will be there, where the multiplexers will be there, so that it will be able to extract the right sum bits. Right, so that's about this red boxes and as well as the black boxes. These green boxes are utilized so as to generate the sum bits. Right, so now I'll tell you. So this particular green boxes, right, it takes in 1 as well as 0. So these green boxes, there will be 2 of them. One takes in the input of 0, carry input as 1. Another one takes in the carry input of 0. So each of these boxes here, are basically, it's a pair of boxes. One takes in an input of 0, the other one also takes in an input of 1. Right, so 1 and 0, and it creates G5, it creates G6 is to 5, it creates 7 is to 5, it creates a 8 is to 5. But because the input is already provided, this is basically G8 is to 0, 5 is to 0, 6 is to 0, 7 is to 0, 8 is to 0. Right, and these will be utilized to generate the sum. Right, because I'm assuming the carry input to be 1 or 0. It's not, need not have to wait for G4 is to 0. Right, in this particular stage, if I'm assuming to be 1, then what is the sum bits? If I'm assuming to be the 0, what should be the sum bits? In fact, in this particular second stage, I will actually create 5 is to 0, 2 G5 is to 0, 2 G6 is to 0, 7 is to 0, 2 such of a pair of them, by taking the input as 1 and 0. Right, moving ahead. So that's what it's going to create. I will have 5 is to 0, 7 is to 0, 9 is to 0, 10 is to 0, 11 is to 0, 13 is to 0, a pair of them. Right, and if it goes to the XOR gate, right, so that I'll get an XOR gate with this 0, an XOR gate with this 1, I'm going to get the sum of the 7th bit, or rather 7 is to 0 will give me 8 bit, with the carry input of 0, the sum 8 bit with the carry input of 1. Now that goes to the multiplexers here to generate the real sum bit, where the select line is coming from 4 is to 0. So this is about the sum 8 bit. Similarly, I should be able to get the S6 bit, where XOR with the 0 bit, XOR with the 1 carry input is going to create the sum of S6 with 0 bit with considering 0, and S of 6 bit with considering 1 as an carry input bit, That goes to the multiplexer. The select line of the multiplexer is this 4:0, which will generate S6. Similarly, if I consider S16, then based on 12:0, which will go to the select line of this multiplexer, the two inputs to the multiplexer is XOR with this particular 0, whatever is the sum created, and then XOR output of the XOR, which is nothing but the sum created with this 1. Right? So I will have that goes to the multiplexer, and then the output of the multiplexer will be S16. Right? So for generating the sum bits, we need this particular green boxes in each of the groups, right? So that considering 1 or 0, it will be considering 1 or 0, considering 1 or 0, it will be able to generate the G, a pair of G, 8:0, 7:0, 5:0, 6:0, or rather 7:0, 6:0, and 5:0, and then that will be provided to the that will be given to the XOR gates to generate the sum bits, and then that sum bits, the pair of the sum bits, will be going into the multiplexer inputs. The select lines will of course come from the real G4:0, and then the select lines here also will come from the real 12:0 whenever it is generated, right? And then it is able to generate the right sum bits. Right, so I have not populated all the sum bits because it will make it very difficult to read. So I have just used some of the sum bits, S16, S14, S8, S6, S5, and then I'm saying that all the other sum bits will also follow the similar sequence. Now, what should be the delay of this? So the delay of this is anyways the first stage, the bit level PNG signals, the bit level propagate and generate signals. The last level, it's a little bit different than that of the previous case. So this TPG is nothing but the bit level, and then I'm saying that it takes in in this particular case n bits. So we will have k groups. Each group is of n bits. So we can say that it is 4 bits or an n bits of the red boxes here, followed by we are interested in S16. So followed by 2 of the red boxes, followed by k minus 2. Here we have made it 4 groups, and we are using only 2 red boxes. So k minus 2, 4 minus 2 will be 2 red boxes. Each of these boxes is nothing but the AND and OR gate. And here, once it comes here, it goes to the multiplexers, and the outputs are of this, the XOR gates considering 0 as the carry input, and XOR of 1 considering 1 as the carry input. Those are made available, and then this multiplexer. So the moment 12:0 is generated after this after this 4 blocks and then these 2 red boxes, the select line. So the delay will also include the T multiplexers, and then S16 will be generated. Right. So we have the critical path like this, this 4 and then this 2, and then this 12 will go here, multiplexer and S16. All right. Here, notice that I have not included the XOR bits here, or rather, so this XOR gate, both 0 and 1 will be there in parallelly running, but we have not included that. The reason is, so I've said that the T XOR is not included in K minus, it's already included in this 2 addition. In fact, the moment this and this is done, right? So this is going to create a pair of 15:0. So this XOR gate will actually happen here, right? Whether it is for 0 or whether it is for 1, right? But my red boxes here are, it is way down than that of the output of the green boxes. Right, these 3 green boxes are the same level as that of, the output here will appear at the same level as that of the output of this. But after that, it has to go through this and then the red boxes, and then it has to go to the mux. Right, so the T XOR gate is not included here because this 2 cases will actually come here. Right, and then the output of the XOR gates, the pair of the, the XOR gates will deliver the output here much earlier than this particular the red box output. And that is the reason why the critical path doesn't include the XOR gate. So the critical part involves this 4 blue boxes, 2 red boxes, and then the multiplexer. So the delay is nothing but this particular expression, where it includes the PG bitwise delay, and then we have 4 TAO and then K minus 2 TAO. In this case, it will be 2 TAO and then one multiplexer. So in terms of making it more generic of k groups and each group of n bits, we will have n TAO and k minus 2 TAO. So hope this is clear. So in this particular lecture, what we had seen is we started with the carry increment adder, and then we looked into the carry select adder. The carry select adder requires a lot of hardware. There are a lot of we assume that the carry input for a particular group will be 1 and 0, and then compute the sum bits. So it will require a lot of parallel and OR gates, and then it is going to generate the pair of sum bits, which will be going into the multiplexer groups. The multiplexer will get a select line, that is the select line will be nothing but generated from the carry out of the previous group. So based on the carry out of the previous group, then we will have the real sum bits extracted. So overall, the carry select adder turns out to be the really fastest. Considering the all other the adders, the carry select as well as the carry increment adder turns out to be the fastest among the group of adders which we had seen, such as carry ripple adder, carry skip adder, carry look ahead adder. Hope you are able to understand this. So thank you for watching this lecture.